You have a prescription.
Yes.
So,
we follow. Yeah.
So maybe would your result depend on this prescription?
Oh, we have tested for different.
You have so many, say, satellite. So what do you really measure? Is measure the velocity in different
the
points of the galaxies?
Yeah, only 40. Yeah, about 40 satellites which have 60 information. That means the velocity, the distance, and the angle position, and the radial velocity, and the proper motion velocity. So this means 60 information, but only 30 or 40 satellites have this information. But when we construct this theoretical distribution function, we use a lot in theory. So this means in theory we use a very large sample in the model. We construct a very precise distribution function, but in measurement, we have only very limited information.
So in your theoretical model, do you have dynamics coming in? Say what is what is the dynamics of the Newtonian?
This is just a velocity.
Just a velocity. So how do they move with each other?
In the simulation, we know all this information. Because this is from the simulation. Very big simulation. I am not going to details. This is a very big simulation with several tens of billion particles, and it's a very big simulation. So now let's go to the application. Let's go to application. And as I said, so in our application, there are 28 satellites with proper motion. Proper motion. And these are all the dots. So blue dots here. And actually there are other satellites. So it's triangles. So as I said, we have about 60 satellites, and in this range, so we have I think almost 50, more than 50 satellites here, or plots here. And as you see, so this is luminosity. This is luminosity of satellites, and this is distance from the center of Milky Way. And you can see this is more bright is negative value. More negative value, more bright galaxies. And as you see, if they are quite distant, then only bright one can be observed, right? So this is more distant and more bright galaxies can be observed. If they are close, then we can measure fainter one, right? So this is very natural, right? And so approximately you can see, so from the observation you can see, so this is almost a line separate, satellite. Above this line, so this satellite have proper motion, and below this one, they cannot be measured. So they can be not measured. So this is approximate one in the observation. And interestingly, so this is just corresponding to the magnitude limit of 16.5. So this means, so if satellite is brighter than this one, then can be measured, otherwise cannot be measured. And this one is more technical one. So according to the detailed observation of Gaia, then we will have this line. This line. So this means the selection effect, right? So more faint galaxies in distant halo cannot be observed. So this is a kind of selection function. Then we must include this one. Okay. And this is the way so we can actually do this. So this is a so-called field space distribution, and in the theory we can include this constraint in here. So yeah, here. So you can do this in model. Yeah, I cannot do. Yeah, cannot go to much details to explain this function, but you can include the incompleteness or selection function in this distribution function, and also you can include the errors in this distribution function. Okay, distribution. This by some convolution. Okay, so from here, then we can infer the distribution function, the value of the mass and the concentration from this Bayesian distribution function. Okay, so this is the way we do, and I think so this is almost the final result we have. So again, so this is from so one is just from satellite. So what we get is here, and the satellite. If we use MC relation being this one. If we use MC relation, then we can get much tighter constraint. And interesting, you can see, so from satellites only, then we have about, this is 1.3 times 10 to 12 solar mass. So this is what we get, and about 15 or 20% of error. If we use MC relation in the cosmology, then we can better constrain C. Especially better constraints on C. Okay, and this is comparison with local many observations I summarized, and most of them are from the dynamics of stars. And you can see, so all of them are quite local. In many cases, quite local. Within this, and here so quite large, errors, and you can see different groups, many, activities going on in those few years. So many different groups, and you can see, so in most of them actually are within one sigma error with our determination. Our determination is this is the central one, and this is the 1 sigma, and this is 2 sigma, and all these points are from other people. So you can see, so it's almost consistent. Not consistent with others. And interestingly, even we don't use concentration mass relation, we can use, say, a set of observation like 1. So you can see, so most of data from 1 to they have combined most observations with other people's observation, then they get this value. If we use this value as a constraint, then what we get in this diagram, so this is the values they get. So this is 1 at all get, right? So if you have, because this is so I just give a few words. So this is their determination is in the central region, right? So this means so they have determined the mass in the central region. If you want to have large head of mass, then you will need a low concentration. If you want to have small, mass, then you need a high concentration, right? So this is something you get. So small mass, high concentration, large mass, low concentration, and this is what they imply in the observation. If you combine this banana with our observation, so this is just a satellite without MC, then what we get is here. So this is much improved, even if you don't use this one. Okay, don't use this one. So don't use this one, then you can also get quite good constraint on both mass and concentration. Of course, if you combine the mass concentration relation, then you can even get better one. You can get even better. Okay.
I was going to ask, what is the visual radius and what is the scale radius?
Sorry.
The radius of halo and the scale radius.
Yeah, because so when you have fixed mass, then you know the radius. So this is the one-to-one correspondence, right? Yeah. So this means so the radius and the mass is one-to-one relation. Then so the scale radius is just the radius of the halo to C, ratio of the radius of the halo to the concentration.
Yes, I understand. But I'm asking the value.
The value.
The number.
So this means about so this is 11 and it's about 300. So means RS is 30. So about 20. Scale radius is 20 of halo, not of galaxy, but of halo. So it's 27 or something. Yeah, 27 or something kilopascal. Yeah. Okay, so this is my conclusion. So it's a lot of information, and so we have demonstrated that the satellites are the better tracer for the Milky Way mass estimation because physics is understood, and also the whole mass of the Milky Way can be well covered. And we have also developed the formula method for including errors and incompleteness. And this is our determination. Okay, determination for the halo mass. So what I want to stress is error in mass is only 15%, and the concentration about 20%. So it's already so very accurate. Yeah, in the determination. So thank you.
I think it's a very nice talk. Yeah, I like this phase-based modeling of the Milky Way is calibrated by embodied simulations. So the actual Milky Way is not isolated system. There's neighboring galaxies, and I heard that actually the halo boundaries of the Milky Way and the halo boundary of the neighbor galaxy, I think Andromeda, actually touching each other.
Yeah.
And your satellites actually reaching the halo boundary of Milky Way already 300 kiloparsec.
Yeah.
So maybe some of the satellites in their outer orbits may be cut out by the nearby galaxies. And I want to know this is an important effect.
It's a very good question. And actually in our paper, we have clarified this. And in our first paper in 2017, and we have tested this effect. So we have compared the distribution function of halos with or without companion. And we found that there is little effect. So yeah, we chose say isolated halos and compare with say Milky Way local group pair, with M31, and we found that effect is very small.
Thank you.
Two questions. One question is, you assume the distribution function is functional energy and angular momentum, and so you assume equilibrium distribution, and so everything has to settle to be time independent. And I was wondering whether this assumption has some question, and that is the first question. And the second question is, have you compared the local measurement of dark matter density to your solution?
Yeah.
Because people measure the local dark matter density near the solar neighborhood, and that is like a 1 GeV per cc or something.
Okay, yeah, good question. So for the first one, actually, I have not emphasized explicitly in my talk. In fact, so we do not rely on at all the assumption of equilibrium, because we construct distribution function from simulations, and in the simulations, it's not in equilibrium. We have not assumed any, the state of dynamics, say steady state, or So we just compare the distribution of the satellites within some region in the simulation to the observation within some region. So this means that this is apple-to-apple comparison, and we do not rely on any assumptions. Yeah. So this is the first one, and the second one is so to me, so the uncertainty. I would say so. First, I would say our measurement is incompatible with local measurement. But I would say that local measurement of dark matter around the sun is very uncertain. I would say, mainly because they have to rely on some Jeans equation there. And as you know, this is not a spherical Jeans equation, but this is axiometric Jeans equation, and especially the boundary condition is very, very difficult to be described, and different assumptions about the boundary can affect a lot in local measurement. And another uncertainty is distribution function. The distribution of baryons, and you have to also exclude baryons, and then it's also uncertain. I think two effects makes local measurement of dark matter around the sun is still very uncertain, in my opinion.
I have a question. So this M. So this M is the mass of the Milky Way, right? So this is a typical galaxy mass, or this is particular to Milky Way. So in your simulation, what defines our Milky Way? The 40-something observations?
No, this is so-called halo mass of our Milky Way. So this is something like this. So Milky Way is here. So this is the mass within this boundary. And the boundary is usually defined as the density, which is 200 times of critical density. So in our case, so we define this boundary is as the local density here, oh sorry, the mean density within this radius is 200 times of critical density. So this we usually call it halo mass, the total halo mass around the Milky Way.
So this is more generic. So if you have other galaxy somewhere else, is it all more or less the same or different?
Yeah, according to this, certainly for different galaxies have different halo mass. Yeah, and the relation is this way. Yeah, so I can tell you. So this is the relation. Okay, so this is the mass ratio. Okay, and certainly you need to times this get the get the stellar mass. So this means stellar mass. And you can see, so something like this one, so it's like this one, so it's here. So you will have different halo mass, different stellar mass. You will have different halo mass. Yeah. If you want to do this, you can use this one. Yeah. To convert. Okay. So this is average, but still there are quite some dispersion. Yeah. This is average, but there are still some dispersion.
Any other questions? Okay. So one quick announcement. So tomorrow, Professor Jin will give another colloquium talk, a completely different topic, and he is focused on like a galaxy survey and cosmology. But it's not here; it's in ASIAA building at the same time. So if you're interested, you're very welcome to attend this talk as well. Okay. So let's turn to Professor Jin again.
Okay. Thank you. So tomorrow I'm really talking about cosmological structures. So it's a much larger scale.